What if you could count how many 1 bits are in the binary representation of every number from 0 to n, in just a split second? Counting bits is a Pattern Mastery 100 in LeetCode favorite because it tests if you really know how to optimize with dynamic programming and bitwise tricks. This problem pops up in Phong interviews and is a launchpad for mastering binary manipulation and efficient array filling. Ready to turn a brute force grind into a one-pass breeze? Let's get started. Let's break it down. You're given a number n. Your task is to return an array. Each position I in that array should tell you how many ones are in the binary form of the number I. For example, if n is 2, we look at the numbers 0, 1, and 2. 0 in binary is 0b0. It has 0 ones. 1 in binary is 0b1. It has 1 1. 2 in binary is 0b10. It also has 1 1. So the final array is 0, 1, 1. Now let's assess our options. A naive approach would use a helper function like bin I. Count 1 for each number from 0 to n. That works but is O(n) log at time. Can we do better? Yes. There's a dynamic programming trick. For any number I, the count of ones is 1 plus count of ones in I and I1. Or, using another pattern, count bits I equals count bits I right shift by 1 plus I and 1. That's because shifting I right by 1 drops the least significant bit, and I and 1 tells you if that dropped bit was a 1. This lets us fill the answer array in O(n) time. Here's the structure. Initialize an answer array of size n plus 1 with zeros for every I from 1 to n. Use ens I equals ens I right shift by 1 plus I and 1 to fill in the value. Return the array. Let's try to implement it using solution 1. We start by creating a class named solution. This is simply the container that holds our method for counting the number of 1 bits for every number from 0 up to n. This line defines our method count bits. It takes an integer n and returns an array. Each position in that array will store how many ones appear in the binary form of the number at that index. So index 0 holds the count for 0, index 1 holds the count for 1, and so on. Here we create an array called res with n plus 1 slots. Why n plus 1? Because we want to store results for every number from 0 all the way up to n. This begins a loop that goes from 0 up to n. For each number I, we will calculate its Hamming weight, the number of ones in its binary representation. Since this loop runs n plus 1 times, this contributes a time complexity of O(n). Inside the loop, we create two variables. X, which will be our working copy of the number I, and C, which will count how many 1 bits I has. We use X so we don't modify I while inspecting its bits. This starts a loop that runs as long as X is not 0. In each iteration, we'll inspect the last bit of X and shift it right to continue checking the rest of its binary form. The worst case number of iterations for this loop is the number of bits in the number, for a 32-bit integer, that's at most 32 steps. Here we check whether the last bit of X is a 1. X and 1 isolates the least significant bit. If it's 1, we add 1 to C. Otherwise, we add 0. This line right shifts X by 1 bit, effectively deleting the bit we just inspected. Now the next bit moves into position so we can check it on the next loop pass. We store the final count C into the result array at index I. This records the Hamming weight for the number I. And here we return the completed array, giving the caller a full list of bit counts. And that's how this algorithm works. It first sets up an array to hold all results, then examines each number from 0 to n, counting its 1 bits by checking 1 bit at a time. Efficient, simple, and elegant. Solution 1. Test case 1. Let's test our function using this input. 2. This value tells our program to compute the number of 1 bits for every number from 0 up to 2, producing an array where each index I stores the bit count of I. Here's what happens step by step. For 0, the binary form is 0, it contains 0 ones. For 1, the binary form is 1, it contains 1 1. For 2, the binary form is 10, it contains 1 1. So the correct output array should be 0, 1, 1. Each position reflects the number of 1 bits after manually counting each number's binary representation. And that's exactly what our program outputs, 0, 1, 1. And the expected result matches perfectly, 0, 1, 1. So the solution is behaving just as intended. So, our implementation is correct. The algorithm successfully computes each bit count by examining binary digits one at a time, efficient and accurate. Now let's try another implement approach using solution 2. We begin by defining the solution class, the container for our optimal dynamic programming approach to counting bits. This method, countBits, takes an integer n and returns an array where each position I contains the number of 1 bits in the binary representation of I. We create an array res of size n plus 1. Each index I will store the count of ones for number I. So it's like preparing a results table where every slot will eventually hold its bit count. This loop runs from 1 through n, computing the bit count for each number. The time complexity of this loop is O(n) because we compute each result in constant time using a formula, not by scanning bits. This single line is the magic behind the optimization. Here's what it does. I1 means we shift the binary representation of I1 bit to the right. This is equivalent to dividing I by 2 and dropping the last bit. The number of 1 bits in I1 is already stored in res I1. IN1 checks whether the last bit of I is a 1. If the last bit is 1, IN1 is 1. If the last bit is 0, IN1 is 0. After computing all results up to n, we return the filled array res containing the bit counts for every number from 0 to n. And that's how this algorithm works. It first prepares an array for results, then uses a clever dynamic formula that reuses previously computed values to calculate each bit count in constant time. Efficient, simple, and elegant. Solution 2. Test case 2. Let's test our function using this input, 5. This number tells our algorithm to compute the count of 1 bits for every integer from 0 through 5, returning an array where each index stores the number of set bits for that value. Here's why the solution works. This optimized approach uses the relationship between a number and its right-shifted version. Res I1 gives us the bit count of the number without its last bit. IN1 adds 1 if the last bit is a 1. So each result is built efficiently in constant time. For example, 001s, 111, 01, 211, 10, 321s, 11, 411, 100, 521s, 101. Putting these together gives 0, 1, 1, 2, 1, 2. And that's exactly what our program outputs, 0, 1, 1, 2, 1, 2. This confirms that the bit counting logic is working exactly as expected. So, our implementation is correct. The algorithm successfully computes bit counts using a fast dynamic relation that reuses previous results, efficient, accurate, and reliable. Let's wrap things up. This problem was all about counting bits efficiently, not just for one number, but for every number from 0 up to n. Breakdown recap. We started by understanding that for each number, we needed to figure out how many ones appear in its binary form. Essentially, we're building an array that shows the bit count for every integer in sequence. Assess recap. We compared two ideas, the brute force way using built-in binary counting, and a smarter dynamic programming method. The DP insight was that the count for any number I can be derived from smaller results, either by using I and I1 to remove a bit or by noticing that shifting I right gives us a related subproblem. This transforms a repetitive process into an ON solution. Structure recap. The plan was straightforward. Start from 0, and for each number, calculate its bit count using previously stored results. This lets us fill up the arrays step by step without recalculating from scratch. Implement recap. We coded this solution on LeetCode, and it executed smoothly without any syntax or runtime errors. Check recap. After running the test cases, the output matched perfectly across all inputs, confirming that our dynamic programming approach worked exactly as intended. The big takeaway? Bit manipulation and dynamic programming make a powerful combo. When you spot patterns that build on smaller subproblems, you can turn what seems like a heavy computation into something beautifully efficient.